Hi everyone, in this video we will continue our discussion on triple integral with an example which will illustrate the use of those 6 possible ways in which we can evaluate a triple integral and how one or the other may be better. So here we are trying to evaluate the triple integral over the region E bounded by y equals x squared plus e squared and y equals 4, with the density function being square root of x squared plus y squared. So let's look at our bounding region first. Again, from Calc 3, you should be familiar with these shapes. Y equals x squared plus e squared is a paraboloid, which is cut off at y equals 4. So what we have is a shape of this form, where this end is a disk. And each of these segments is a circle because it's x squared plus z squared. This is y, z, and x here. And this surface is y equals x squared plus z squared. This point here is 4. That's the y equals 4. And if you look at, let's suppose we project it to the x-axis, right? So we have a two different borders of this equation, so to speak. And let's suppose I project it into xy plane. So project to xy. If I project this to xy plane, what I get is a parabolic region here. So if I project this to xy plane, I end up with a parabola where we have y equals 4 being cut off, and this is y equals x squared. Why is that? Well, plug in z equals 0, you get y equals x squared. So this will be the region that we are working with. So if I do it this way, then my integral gets set up as first integral, well, x squared plus e squared. Projecting to xy means I'm doing dz first. And where is z going from? Z is going from, so if you have this, then this equation, this is y minus x squared square root, and the bottom half of this is the negative of y minus x squared square root. So this is going from negative y minus x squared to y minus x squared, and then we're going from y equals x squared to y equals 4, and then we're going from x, whatever these points are, negative 2 to 2. This is very difficult, right? So this is a very difficult integral. It's difficult integral to solve because it's z squared in with an x squared. So if you recall from your previous integration stuff, this is going to give me an arctan. Then I'll have an arctan of z over x, and that's the limit I'll be putting into arctan. So which means for the next integral, I will have an arctan of square root of y minus x squared over x. Kind of crazy stuff. Finding integral of that. So now which is where you will be like, it's not that it's not doable, but because you're working with triple integral, at this point you should ask yourself, wait a second, maybe one of the other remaining 5 ways may be easier to do. And indeed, in this case, it will turn out that will be so. And the way to sort of figure that out is recalling that, so just look at the projections, right? And usually it's the projection that kind of gives you an idea of what's going on. So let me redraw this as 4. We get y equals x squared plus y squared, x squared plus e squared. So if I take the projection down, it's a parabola. If I take the projection across, it's still a parabola. But if I take the projection in this direction, it's something different. It's a circle now. So the idea is that, if I project it this direction, then I get an interesting shape, which is a circle. Whenever you get circles, or wherever you can get circles, is where you want to go, because polar coordinate. When you have circles, you can use polar coordinate, things become easier. So in this case, of the 3 choices of projection, one of them is clearly better because it gives me a circle. What is the equation of the circle? When we project it to the xz plane, y is 0. And when y is 0, we get the circle to be x squared plus z squared. So this equation of the circle is x squared plus z squared equals 4. -2 and 2. So in this case, now my first setup is square root x squared plus z squared. But my first is dy. And what is y changing from? Y is going from x squared plus z squared. So from here to, x squared plus z squared, which is this, to this disk, which is at y equals 4. So immediately you will notice that the x squared plus z squared, and this is dy, so which means we won't get that arctan and all of that stuff that we're trying to avoid here. And then once we're done with that, there will be some element dA, and we will worry about it afterwards. Now, because this region D is more helpful in polar, we're just gonna use polar. Right, so we're going to use polar. If we use polar coordinate, here's what happens. So this becomes, so when you do the integration, this is just going to be square root of x squared plus z squared, and then a 4 minus x squared plus z squared dA over d. Converting this, you get 4 minus r squared. You get an r. You get a r dr d theta. And you get r going from 0 to 2, 0 to 2 pi. So note here, we're using the polar coordinate on the xz plane. Okay, so this is xz plane, which means that when we use polar, we have x squared plus z squared equals r squared. So not x squared plus y squared, because our circle is on the xz plane, not on the xy plane. And from here, it's just a matter of getting the integration sorted out. In fact, you can separate this out. So you have 0 to 2 pi d theta, and of 0 to 2, 4r squared minus r 4 dr. This gives you a 2 pi, and then the second one gives you a 4/3 8 minus a 1/5 32. 2 pi, 32 over 3 minus 32 over 5, which is 2 pi over 15 times 32 times 2. So 64 becomes 128 pi over 15. So if it doesn't work in one way and you get like some nasty integral which you don't want to work with, maybe try another way. And because you know that, now you can even avoid that by looking at the figure. Just by looking at this, you can be like, well, I get a parabola, I get a circle. Those are the three options. What's easier to work with? A circle. So let's go with the circle. Changing the order of integration. So again, this is the xy projection, right? So there are 6 possibilities. And because there are 6 possibilities, it means that if you want to go from one to the other, you have 5 other ways in which you can work. So here's a distinct example. So for example, here we're starting with dz dy dx, right? And we are trying to find what the different forms are going to look like. So let's look at what are we working with here. We're working with z equals 0 to z equals y. Okay, z, y, x. Let's try to draw the figure of what we're working with. Z goes from 0 to y, so we have z equals 0 to z equals y. z equals y is going to be some line. Y goes from 0 to x squared, so we have a shape which looks something like this. So you have this, which is z equals y. You have a y equals x equals 1, and you have a y equals x squared. So what are the three different projections, right? The three different projections you can do here are the following. On the xy plane, you will get not a triangle, but with a curved hypotenuse. On the yz plane, you will get a triangle, and on the xz plane, also you will get something similar. Like, so you will get y equals x squared and x equals y. Here you will get z equals 1 and y equals 1. Here you will get x equals 1 and z equals x squared. And so depending on which of them would be easier, you can sort of rearrange stuff and work with it. So there are 6 of these. One of the applications similar to similar to what we had with double integrals, which is if you take the density function to be 1, so constant everywhere, and you evaluate the double integral, then you get the area, right? So triple integral, same thing. If the function is constant, then the triple integral is a volume. So you can be asked to find the volume of things just by given their equations. So find the volume of tetrahedron bounded by the planes x plus 2y plus z equals 2, x equals 2y, x equals 0, and z equals 0. So which means all you have to do is figure out the limits. If you figure out the limits of the triple integral, then you're just finding the integral of one constant function, and that's going to give you your volume. Let's look at the shape. Again, recall from Calc 3 that these are specific planes here. When they cut through, they're going to look something like this. So we have x plus 2y plus z equals 2. And we can find some of these coordinates just by plugging in some values here. X0, y0, z is 2. So 0, 0, 2. x0, z0, y is 1. That's here. And y0, z0, oh, we don't have that because you have x equals 2y. So we need, it has been cut off by x equals 2y, where x equals 2y is this plane. So we got to figure out this intersection point of x of these two planes. If x equals to y, this point is going to be 1, 1/2, and 0. So this is our shape here that we are working with. So if I look at the projection, I'm going to project this down into xy plane. Down on the xy plane, it's a nice, wrong pen. On the xy plane, it's a nice triangle. So if I project it down on the xy plane, I get a region that looks like that, where this is 1, 1/2, and I can go this way. This equation is y equals x over 2 because x equals to y, and this equation is x plus 2y equals 2 because z is 0, or y is 1 minus x over 2. So finding the volume simply amounts to doing this 1 dz first because I'm projecting to xy. Where does it go? It goes from 0 to the plane, which is 2 minus x minus 2y. Then it goes from x over 2 to 1 minus x over 2, and lastly x goes from 0 to 1. So the first one gives me 2 minus x minus 2y, dy dx, dy dx, x over 2, 1 minus x over 2, 0 to 1. So I get a 2y, so 1 minus x minus 2 minus x minus 2 gives me 1 minus x. Same thing again, 1 minus x. Finally y squared will be 1 minus x over 2 squared minus x over 2 squared. So maybe let's try to resolve all of this algebra stuff first. This is going to be 2 minus x times 1 minus, let's FOIL it out. So 2 minus 2x minus x minus plus x squared minus, what is this going to give me? This is 1 plus x squared over 4 minus x squared over 4. So 1 plus x. What's that going to give me? 2 minus 1 is 1. Negative 2, this cancels. 1 minus 2x plus x squared. Dx 0 to 1, that's a 1. That'll be 1. That'll be 1/3. So the volume is simply 1/3. Okay, here's a problem that you can try as extra credit again. So it's going to be extra credit slash your video quiz participation. That is, to make sure you're watching the videos and, working along and doing the problems, and you can submit this via email. That's it for this particular video.